Welcome to organic chemistry. Organic chemistry is often referred to as the chemistry of life because biological compounds like DNA, proteins, and carbohydrates are organic molecules. In this chapter, we are going to look at some bonding characteristics of organic molecules, and we need to remember that organic molecules are constructed primarily from carbon, hydrogen, nitrogen, and oxygen. So those are going to be the elements that we tend to look at the most. We're also going to review several aspects of atomic and molecular structure that we covered in general chemistry. I just know that it's been a minute, so we're going to go back and look at some of those and just kind of dust off those brain cells. And some of the topics specifically we're going to look at are ionic and covalent bonding, the basics of Lewis dot structure, and resonance theory. Then, in the rest of the chapter, we're going to focus on organic molecules, looking at different types of shorthand notation that organic chemists use. And we're going to also look at common bonding arrangements called functional groups that we see in organic chemistry pretty frequently. At the end of this chapter, we're going to apply some of these ideas, especially functional groups, to certain classes of biomolecules, amino acids, monosaccharides, and nucleotides. With this early introduction to some of the basic aspects of biochemistry, my hope is that you'll appreciate the relevance of organic chemistry to biological systems, specifically if you are interested in biological systems. So let's go ahead and jump in and talk about organic chemistry. So organic chemistry is just the branch of chemistry involving organic compounds. Now, in the late 1700s, organic compounds were defined as compounds obtained from living organisms, like glucose or testosterone or deoxyribonucleic acid, which are all shown here, right, in this image. So this was in the 1700s, right? Organic compounds came from living systems, right? Now, there was a theory at the time called vitalism. Okay, where it says kind of only living systems could summon up a mysterious vital force needed to synthesize these organic compounds. And so all other compounds, including ones synthesized in the lab, were defined as inorganic. So when we talk about vitalism, right, these were basically compounds from living systems, right? And inorganic compounds were defined as compounds that come from everything else. Right? So this definition was refined in 1828 by a chemist named Frederick Wöhler. Okay? And so what he did is he synthesized urea. And now remember, urea comes from living compounds. And so what he did was he took ammonia cyanate, which is shown right here, and it was what they considered to be inorganic, okay? And he heated it and formed urea. Now, urea is a major component of mammalian urine, and obviously was defined as organic, but ammonia cyanate here was inorganic. And so vitalism couldn't account for this distinction between organic and inorganic compounds. And so gradually chemists arrived at our modern definition, which is an organic compound contains a substantial amount of carbon and hydrogen, whereas an inorganic compound does not. Okay. This definition is not perfect, since some carbon-containing compounds, like carbon dioxide, are also considered inorganic. In chemistry, we always talk about 5 big branches. We have biochemistry, organic chemistry, inorganic chemistry, physical chemistry, and analytical chemistry. General chemistry really focused on inorganic chemistry, physical chemistry, and analytical chemistry. So organic chemistry is very separate. It's really going to focus on carbons and hydrogens and the types of reactions they can do. And those should feed into biochemistry, which you will take if you so choose next year. So, organic compounds have been around a long time in ancient civilizations. Royal purple, which is also called Tyrian purple, was a natural dye that was attained by the ancient Phoenicians from the aquatic snail. And so about 10,000 of those snails had to be processed to get a single gram of the dye. And so that's something that we talk about a lot. If you were in chemistry and art, we talk about, but organic compounds have been around for a long time and have been used by people. So that's just kind of an interesting tidbit. So we said most of these are going to focus on carbon. And so the big question, of course, is why carbon? I also want to point out something really quickly. You're going to notice that I have these section numbers here with the same title as the section in the book. This is to help you easily reference where our notes are to where we are in the book. So you can also use this as kind of a guideline to see where we are if you want to follow along in your book while we are looking at some different lecture notes. So why does carbon play such a central role in the chemistry of life? So we're big carbon molecules. We've got all of organic chemistry, which is dedicated to carbon. And so we get to ask my favorite question, which is why? Why is carbon so special? Well, first off, carbon is capable of forming just an incredibly diverse amount of compounds. And so there's a couple of reasons why it can do that. First off, the carbon atom can form 4 covalent bonds to other atoms, especially other carbon atoms. Okay. Now, so because of this, that means that carbon atoms can link together in chains of almost any length. And so that's what we're seeing here. We can make these big chains. Notice that carbon's making 4 bonds. 1, 2, 3, 4. The other thing they can do is also make rings of just various sizes. So carbon atoms can link together in chains of almost any length, right? And they can make branches or rings. Now, not only this, but carbon atoms are capable of forming single bonds, but also double or triple bonds. So there's a lot of versatility in the bonds they can form. And so you can see this here. Here's a double bond and here's a triple bond. And then the kind of finally here, why carbon? The ability to form bonds, 4 bonds specifically, means that branching can occur. And so you can now get really large structures with the branching that can occur. So these characteristics make possible a tremendous amount of compounds, even with a relatively small number of carbon atoms. So to date, tens of millions of organic compounds are known, and that list is growing rapidly as we continue to discover or synthesize these new compounds. So one of the things that we do in organic chemistry, because there's so many compounds, is we tend to put compounds into groups based on their functional group. Because what we find is that molecules with the same functional group tend to react in the same way. So what we're going to do through organic chemistry is really focus on how to categorize these molecules and lump them into big categories so we don't have to memorize quite so much. Now, maybe the burning question in your heart is, what about silicon? Silicon is right down in the periodic table from carbon. So silicon has a lot of the similar functionalities. Well, so silicon is found just underneath carbon on the periodic table. Well, so elements, I just want to remind you, elements in the same group of the periodic table, and that's, remember, the columns, tend to have the similar properties. So silicon can form 4 covalent bonds. It gives it the same potential for diversity as carbon. But really the answer comes down to stability. All right. And so these two reactions here show that carbon and silica can really do the same kind of chemistry here. But again, the answer comes down to stability. The difference lies in the stability of bonds that carbon forms versus those that silicon forms. And so what we mean by that is carbon is going to form more stable bonds. And the reason is that there's less energy needed to break the silica bond as compared to the carbon bond. And so what that means is that carbon-carbon bond is stronger. Right? And so the strength of typical bonds involving the carbon atoms really helps these biomolecules that we're going to study remain intact. And that's essential for molecules to store information and provide cellular structure. And so the compounds that are based on silica or silicon would have been much less stable. Let's entertain the idea of silica atoms replacing carbon atoms in biomolecules just for a second. And so I mentioned that these were two chemical reactions that we have, but look at this. This is glucose, right? So glucose is broken down by our bodies through cellular respiration. And now this extracts energy, and this is the overall reaction for it. So if you've taken biology, you should recognize this. One of the byproducts is carbon dioxide, which is exhaled. So that's kind of our waste product. If the molecules of life were based on silica, right, would be the glucose analog, Si6H12O6. And the byproduct here would be silica dioxide, which is a solid and is the main product of sand, and in the crystalline form is known as quartz. So our waste byproduct would be a solid, and that would be really hard to excrete in a way that CO2 is very easy to excrete. We just exhale it. And so that's also a big reason that silica doesn't work. So let's talk more about bonding capabilities and structure. So in the previous section, we saw that carbon's bonding characteristics give rise to a large variety of organic molecules. And those bonding characteristics and the bonding characteristics of really all atoms are governed by the atom's electrons. So electrons are going to be really central to organic chemistry. In this section, we are going to look at the nature of electrons in atoms. We're going to review the basic structure of the atom, like the role of atomic orbitals and shells. And then we're going to review some rules governing electron configurations that distinguish between valence electrons and core electrons. And so we talked about those in Gen Chem, but we're going to go back and review those. So at the center of an atom, which is shown right here, we have a positively charged nucleus, and that's composed of protons and neutrons. Now, surrounding the nucleus is a cloud of negatively charged electrons, and these are attracted to the nucleus by simple electrostatic forces. Now, I want to remind you, electrostatic forces are just the interactions of oppositely charged particles, okay? So individual electrons are really small. They're so much smaller than the nucleus. But the space that electrons occupy is really, really large. We call that the electron cloud, and that can be seen here. Basically, what we know is that the size of the atom is essentially defined by the size of its electron cloud, and most of the electron cloud is empty space because the electrons are so small. So electrons are small, but they can move in this really relatively large space around the atoms. So I want to review the structure of atoms just really, really briefly. When we talk about an atom, I want to remind you, an atom has no overall charge, okay? And so if you look at the table here, this is table 1.1 in your book, this is going to list the mass and charge of each elementary particle in an atom. So we have protons, neutrons, and electrons. Notice that when we look at the mass of protons and neutrons, relatively, they're about the same, 1 to 1. But I want you to notice that this mass is much greater than the mass of an electron, which is 0.0005. Okay, so electrons are really small comparatively to those neutrons and protons. Now, as I mentioned, an atom has no charge. So what that means for us is that the number of electrons, right, equals the number of protons in a nucleus, okay? Now, that number of protons in the nucleus is defined as the atomic number, which we can look at the periodic table and see, and we represent that atomic number with a Z, okay? Now, so if we were to do an example, right, and look at carbon, the atomic number of carbon is 6. And so what that means for us is that carbon has 6 protons and 6 electrons, okay, because it's neutral. Electrons are negatively charged, protons are positively charged. Now, if the number of protons and electrons are unequal, then that entire species is called an ion, and it's going to have a charge now. The only thing that can change is the number of electrons. So when we look at this, you can have an anion, right? And that's negatively charged, and it's going to have more protons than electrons. So that's negatively charged. And we're familiar with this. This would be like a hydroxide ion, right? That's negatively charged. You can also have a cation, and this is positively charged. And what we see here is, and I got those backwards, so hold on, let me fix that. Got real excited there for a second. Okay, so an anion here has more protons than electrons. It's negatively charged, right? An example is OH minus. And then the cation is positively charged, and it's going to have more protons than electrons. And remember, we said things like cats have paws, so cations are positive. And so that's some things to help you kind of remember that. But that's just kind of a throwback to general chemistry. So let's do an example problem. One of the things that you're going to notice through this book, which I absolutely love, is we're going to have a sample problem, but we're also going to have some things to help us think about as we answer problems. So these are going to be our problem solving techniques. And so we'll be able to walk through these step by step, very similarly to what we did in Gen Chem, but we don't deal with as much math. And so we're gonna try to rationalize through it in the same way. So how many protons and electrons does a cation of carbon, of the carbon atom have if its net charge is positive 1? And so we're going to say, okay, hey, look, we've got a carbon atom and its charge is positive. And so here are some things you need to think about. So how many protons are there in the nucleus of a carbon atom? So we always want to start with protons. Remember, protons aren't going to change. And so we are going to look at carbon on the periodic table. We're going to look at the atomic number, and we're going to see that the atomic number there is 6. And so we can say, hey, look, that carbon atom has 6 protons. And then we're going to ask, does a cation have more protons than electrons or vice versa? And so the answer here is that a cation has more protons. Okay, that's how it gets its positive charge. And so what does that net charge tell us about the number of protons and electrons? Well, that +1 charge indicates there is one more proton than electrons. Right? So if carbon has 6 protons and we know protons can't change, and the only thing that can change is electrons, then we would say, okay, it would have to have 5 electrons so that that charge was positive 1. And so that's how we can determine the number of protons and electrons in an atomic atom. Now, let's talk about where these electrons are. So we know that electrons in an isolated atom hang out in atomic orbitals, right? So electrons are found in atomic orbitals, okay? And what we also know is that the exact location of an electron can't ever be pinpointed, okay? But an orbital describes that region of space where the probability of finding a given electron is really, really high. So we can say with high probability, we can find an electron in a space. And so I love this analogy, but we just kind of view orbitals as rooms that house electrons. So if you think about a molecule or an atom as a house, then we're going to find certain electrons in certain orbitals, much like we would find certain people in your house in certain rooms. So let's look at and review some of the basic properties of atomic orbitals. So one of the things we know is that atomic orbitals are going to have different shapes. So remember from Gen Chem, we had the s orbital, and it's going to have a spherical shape. And the p orbital here is a dumbbell shape. And then we also talked about d and f orbitals, but because we focus on carbon, and if you remember carbon, the electron configuration, we only have s and p orbitals because we only have 6 electrons. So if we remember back to that electron configuration, which we're going to talk about, it's 1s2, because we have 6 electrons, 1s2, 2s2, 2p2. And so that we're only really going to stay here in the s and the p orbital, okay? And so we also know that atomic orbitals are organized into shells, right? And this another thing that we can talk about with shells is we know that's their energy level, okay? And when we talk about these shells, we can see that, for example, in 1s, 2s, 3s, we're going to increase orbital energy as we go up, okay? And so these shells are also called the principal quantum number, and that's N, okay? And that's the number that's shown kind of right here in front of the S. So the S tells us the shape, it's a sphere, and then the number in front of the S tells us the principal quantum number. Notice the size increases as you go up. So as our principal number, quantum number increases, the size of the orbital also increases as well. So up to 2 electrons are allowed in any orbital. So remember in Gen Chem, a lot of times we showed them like this, right? Where one had to spin up and one had to spin down. And I already mentioned this, but with increasing shell number, the size and energy of the atomic orbital also increases. And we also know that within a given shell, an atomic orbital's energy increases in the order of S, P, D, F, and etc. We only really go to F, but to etc. Okay? Now, there are an infinite number of shells in an atom because we just kind of assume that this number N can go from 1 to infinity. In reality, it goes from about 1 to 7, okay? But that's just because, we haven't quite discovered anything else. So in the first shell, when we talk about this, where N equals 1, and so that's the 1 in front of the S, it only contains the S orbital. Right? In the second shell, where N equals 2, we get 1 S orbital and 3 P orbitals. So we end up with 2S, but then we remember we have 2P, and we can have 3 different directions of P, so we call that PX, 2PY, and 2PZ, right? And then the third shell contains like 1s orbital and 3p orbitals and 5d orbitals. But again, we're really just going to kind of hang out in this 1s and 2s orbitals in organic chemistry. Now, I want you to notice this first shell here can only contain 2 electrons, right? There's only one shell. And so that's called, or one orbital in the shell. And so that's called a duet. Now, this second shell, this can contain 2 electrons. This can contain 2 electrons. This one can contain 2 electrons. And this one can contain 2 electrons. And so this can have 8 electrons, and we call that an octet. Now, the third shell can contain up to 18 electrons. And again, you can look at that when you get into larger atoms, mostly focused on in inorganic chemistry. Now, with increasing shell number, as we mentioned, the size and the energy of the atomic orbitals increase. And you can, of course, see that in the figure there. And then within the given shell, the atomic orbitals increase based on SPDF. So the energy there. So for example, the S here has a lower energy than the P does. So that's some things that just to remember. Now, I've already kind of talked about this, but the way that electrons are arranged in these atomic orbitals is called the atom's electron configuration. And so we've already talked in general chemistry, particularly a lot about electron configurations. Okay. And when we talk about these, we can have different electron configurations. The most stable electron configuration has the lowest energy. This is going to be an underlying theme in organic chemistry. If something is stable, it's got the lowest energy. If it's unstable, it has a higher energy. So the most stable, lowest energy electron configuration is called the ground state configuration. Okay. And so electrons occupy the outermost shell, and that's got the highest energy, are called valence electrons. Now the rest are core electrons. So knowing an atom's ground state configuration is really important because it's going to give us insight into the atom's chemical behavior. So for example, if we know the ground state electron configuration of an atom, we can really distinguish between the valence electrons and the core electrons. And the reason this is important are the valence electrons are the ones that are involved in bonding. And they're the ones that are involved when we talk about reactions occurring. It's those electrons that move when reactions occur to form new bonds. So that becomes really interesting to us. So if we look at the kind of energy diagram that's shown here, this is for carbon. And we look here at carbon and we know, I don't know what I just did, so we'll just ignore that. We know that carbon has 6 electrons, like I mentioned before, and it's 1s2, 2s2, 2p6, okay? Sorry, 2p2. And that's shown here in this energy diagram. Now, the core electrons are going to remain in those lower energy shells of the atom. So that means for carbon, these here in this 1s are our core electrons, okay? And the valence electrons are going to occupy those highest energy shells. And so for our carbon atom, these are our valence electrons, right? And so we can look here and we see the highest principal quantum number is 2. And so that's got to be the outermost shell. That's where our valence electrons are. And so that's what we see there. We can use the periodic table to really quickly determine how many valence electrons an atom has. It's just the number of valence electrons in the same group as the atom's group number. So remember how carbon is in group 4, or if you have an older periodic table, it's group 4. Some newer periodic tables will show 14, right? We know that that means that carbon has 4 valence electrons. So that's a really quick way for us to figure that out. Now, we learned electron configurations. We had some rules that helped guide us. And so here were our 3 rules. And so I just want to review these. The first rule was the Pauli exclusion principle. Which just said that no more than 2 electrons can occupy an orbital, and 2 electrons in the orbital must have different spins. And so that's shown here, right? Here's the line that represents the orbital. It's the 1s orbital. And you can see that there's a spin up and a spin down. Now, one of the things that I don't love about this is it's showing these as a double-headed arrow. We tended to show them in general chemistry as a single-headed arrow up and down because most arrows that are shown that are single-headed stand for 1 electron and double-headed stand for 2. So either is fine when we're doing orbital diagrams, but when we transition to do mechanisms later, that's really going to matter. So I just wanted to point that out. The next rule is the Aufbau principle. Which states that each successive electron must fill the lowest energy orbital available. So that just means we got to fill the lower energy orbitals before we go to the higher energy orbitals. So we got to fill 1s before 2s and 2s before 2p. And then the third rule is called Hund's rule. It's my bus seat rule, right? Which says before a second electron can be paired in the same orbital, all other orbitals at the same energy must contain a single electron. And so what that means is that, look, these three are at the same energy. So if you only had 3 electrons, they've got to be in different orbitals. We can look at that back with carbon. If we think about it, it's 1s2, 2s2, 2p2. So we've got 1s, we have 2 electrons. We have 2s, we've got 2 electrons. But when we look at 2p, 1 electron is going to be in one orbital and another electron is going to be in the second orbital. They're not going to be in the same orbital. They want to spread out. So let's go on and do an example for something that's not carbon. So it says, write the ground state electron configuration of the nitrogen atom. How many valence electrons does it have? How many core electrons does it have? Well, when you solve this problem, you need to look at your periodic table and figure out how many total electrons there are in the nitrogen atom. So when we look at nitrogen, we're going to see the atomic number for nitrogen is 7. So it's going to have 7 total electrons. In what order are nitrogen's atomic atoms orbitals filled? Okay, so we've got to put 7 electrons in atomic orbitals. They're going to go in the s orbital first, 1s2, 2s2, and then the rest are going to go in the p orbital, 2p3. We can look here and see that nitrogen's valence electrons, because it asks, what is nitrogen's valence shell and where do its core electrons reside? Nitrogen's valence shell is the one with the highest energy. It's going to have the largest number here, and that's 2. So the valence shell here is the second shell. So that means there are 5 valence electrons. Those are the ones in the outermost shell. Then anything that's not in the outermost shell, which we show right there, are our core electrons. So it has 2 core electrons. And so we can use these electron configurations for us to figure out how many valence electrons do we have and how many core electrons do we have. Now remember, we can also figure this out using the periodic table. So you can look, you can see nitrogen is in group 5, and it's going to have 5 valence electrons because it's in group 5. So there's 2 ways to solve this problem. Use either one you want, but the periodic table is just as useful as far as what we're doing in organic chemistry as using the ground state, the electron configuration. But notice this question specifically asked how to write a ground state electron configuration. So you should know how to do that as well. So in this screencast, we have reviewed electron configurations. We've reviewed atom structure. We've reviewed where electrons are. In the next screencast, we are going to start talking about how electrons form bonds.